Good morning. Thank you, Chairman. My talk will be about the characterization and reliability of gallium nitride amps for high power and high temperature applications. This is the outline of my presentation. I will briefly introduce the standard aluminum gallium nitride amp structure and the high performance GaN amp solutions. Then I will describe our work on the copper gate gallium nitride amp and the switching behavior measurement setup realized. This is a typical cross-section of the aluminum gallium nitride amp. It belongs to the field effect transistor family, and the advantage of this structure is the formation of an high mobility two-dimensional electron gas as conductive channel controlled by a Schottky junction. So the absence of doping in the conductive channel and in the barrier, in the device barrier, translate in a high conductivity without mobility degradation due to impurity scattering. The best gallium nitride-based technology on high electron mobility transistor is nowadays implementing some technological solutions like the silicon nitride surface passivation, the introduction of a field plate structure, and the gate recessing techniques. But what about the Schottky gate contact? Properties like a high Schottky barrier rate, a threshold voltage stability, and a low leakage gate current are properties that have to be achieved for a further increase in performance and reliability. So for these reasons, someone have already studied the introduction of innovative gate metals in the gallium nitride amp technology, such those here reported. Also, the copper was already involved in the gallium nitride amp technology as the Schottky metal, and the results from the literature are here reported. A gate leakage current 2 orders of magnitude lower with respect to a standard nickel gate device, an higher Schottky barrier rate with respect to the standard nickel gate device, and very interesting small signal parameter. So aim of our work is to evaluate the large signal performance by comparing a standard copper gate gallium nitride amp with a standard nickel gold gate amp fabricated on the same wafer and in the same technological step, with the only difference in the Schottky contact formation. The first measurement proposed is the gate leakage current for both devices reported on a semi-log graph. As can be seen, the copper gate device obtained a gate leakage current 3 orders of magnitude lower with respect to the nickel gold gate device. And looking for small positive biasing regime, the copper gate device seems to have a higher Schottky barrier rate. This is in agreement with the previous results already reported in literature. The IV characteristics were obtained by using both DC and pulsing biasing signals, even though the DC component between the devices are quite similar. The pulsing component are very different. The nickel gold gate device show no current collapse, while in the transient behavior some trapping phenomena prevail, generating a critical current collapse for the copper gate device. Concluding the large signal characterization, here are presented the RF power measurements conducted at 2 GHz and in the same biasing conditions. The nickel gold gate device yielded a saturated output power of 1.2 watt per millimeter with a maximum power added efficiency of 46%. The copper gate device confirms the expected not good behavior, obtaining a saturated output power of 31 milliwatt per millimeter and an efficiency of about 3%. So From the experimental results, the passivation process was the same for both devices, and the absence of current collapse for the nickel-gold gate device suggests that no significant carrier trapping phenomena are affecting the access region between source and gate drain. So this substantial difference is probably due to some trapping phenomena affecting the copper-argon Schottky junction. So we have tried an interface trap characterization using an IDVGS measurement in this way, connecting the drain terminal through a 50 ohm resistor to a 3 volt constant power supply, then pulsing the gate terminal from 0 volt to negative voltage values with a period of 30 seconds and pulse width from 5 microseconds to half a second. What we found is something like this: a sharply decrease in the drain current for the nickel-gold gate device, while the copper gate show very long transient. Combining the IDVGS values, these are the IDVGS measurements. There is no discrepancy between the DC and pulse characteristics for the nickel-gold gate temp, while the copper gate device confirms the expected trapping phenomena previously observed, with a sort of modulation of the drain current for small negative voltage values and a not complete depletion of the channel for high reverse biasing. So, in summary, the introduction of copper as gate metal in the standard GaN-M technology was evaluated, comparing a standard nickel-gold gate device with a copper gate device. The presence of a drain current collapse could be explained as an interface trapping affecting the copper-argon interface toward the argon barrier, and numerical simulations conducted on the test structure and not reported here qualitatively support the presence of a trap level with an activation energy of about 43 eV, responsible for the drain current collapse observed. During the second part of the last year, in order to evaluate the switching behavior of our devices, we have implemented a switching behavior measurement setup using a boost DC-DC converter, here presented in schematic and PCB, and we have evaluated the behavior of different GaN-Ms, yielding output power up to 2 watt and efficiency ranging between 60 and 80%. Here is reported a comparison between two different devices, very different in their technology. The wider devices show a higher drain current, and the silicon carbide substrate allows a higher heat dissipation, so a lower on-state resistance and then a higher efficiency over more frequency range. So in the next year, from Monday, I will be with the EC department of the Ohio State University in Columbus, Ohio, under the supervision of Professor Siddharth Rajan. I will work on the fabrication and characterization of gallium nitride AMT for power application. I'd like to thank my tutor Alessandro Chini for this great opportunity, and all of you for your attention. Thank you.